All right, let's start. So in this week, we are going to learn functional testing. And functional testing is also known as black box testing. So today we will cover these three topics. So first, we will have an introduction to function testing. And then we will learn two function testing techniques. So first, let's jump into the concept of black box testing or functional testing. So functional testing is actually normally considered as a form of black box testing, and as indicated by the name of black box testing, we don't care about the internals of the target system we have tested. So we treat the entire system as a black box, and we feed in inputs and we observe the outputs. So you may think, okay, this sounds very simple, right? So do we have anything to learn here? So actually there's a lot of content to learn. So black box testing is done from the customer's point of view. And actually in our last week, I think one of you, but not here today, one of the students asked me whether can we have more code in the slides. But unfortunately not for today, because we are doing black box testing and we are testing the target from the customer's point of view. And as a customer, you don't have access to the source code, right? And because we are doing black box, we don't care about the source code, the actual implementation. And this, so why does black box testing also called functional testing? It's because we aim to test the functionality of the program according to the specifications. So this type of testing is also known as specification-based testing. So here, when we talk about specifications, we need to know what is exactly a specification. What's the difference between a specification and a requirement? If you have done the software engineering workshop here, you may have encountered the term of requirement engineering. So when we build a software, before we actually write the code, we need to be clear about the user requirement. So requirement is more like what we expect the program to do, and under what conditions do we expect the programs to do something. And that is called requirement. And for specifications, as indicated by the name, so it is more specific. So specifications is actually related to how the program will fulfill these properties of the requirements. So it is more detailed. So you can imagine a requirement could describe how each function works, what outcomes to be expected, and how the errors are handled by the program. So this is specification. So let's have a look at this example here to have a better understanding of the difference between specifications and requirements. So let's consider this scenario of a password input field. So the requirement should be the user shall set a password to control account access, and this is the requirement. What about the specifications? So can you think of some restrictions or conditions or descriptions about this requirement? Can you add in more details for this one? Let me give you an example first. So this example is to check the length of the password. So the password should be longer than 8 bytes and smaller than 16 bytes. So what else conditions can you come up with? Yes, yes. We can also have restrictions about the actual content of the password. So we should, one of the specification could be like this. The password shall contain at least, like in this case, one uppercase, one lowercase, a number, and a special character. And if we are implementing on the backend, we can also have some restrictions, like the password should be hashed when stored in the database. So it shouldn't be stored as a plain text. So now we know what's the difference between a specification and a requirement. And functional testing is about deriving test cases based on the specifications. So what is the rationale of this functional testing? So as I just mentioned, we want to derive test cases from these detailed specifications. And remember, in our last lecture, we have covered 6 principles of testing. And these principles are not just some kind of boring concepts you learn for every course, but it is you will have some callback of the previous concepts from time to time. And let's make a guess which principle is most related to functional testing or black box testing. Do you still remember the concepts of these principles? Actually, the most related principle is called partition or divide and conquer. So why is partition here important? It is because we are doing black box testing. We know nothing about the target program. What we can only control are the inputs, and what we can only observe are the final outputs of the target program. So, but as we know, the input space and output space could be infinite. We could have a very large input space. We could have a very large output space. So that's why we need to somehow divide and conquer. So here are some more details. Okay. I think maybe I need to change the mic. Hello. Oh, I think I muted the wrong device. I hope this won't affect the lecture recording and live stream. And we do have live stream online now for this course. And talking about the rationale of doing functional testing, why is it related to the principle of partition? It is because the input space of a program is nominally infinite for most of the programs, unless your program only have 2 buttons. So normally it's infinite. And even this is true even for some seemingly very simple programs. For example, like this slider captcha. So do you think the input is only like how the position of the slided piece of image? It's actually not, because this type of captcha could be easily solved by automated bots. And what some more advanced captcha programs do is they don't check, instead of checking whether the image is in the correct position, they check the process of sliding the captcha. So normally a human won't use a very average or very smooth speed to slide this, and a bot will do it smoothly normally. So instead of just checking the position, the final position of this small piece of image, it will also check how does the user slide this this thing. So as we can see, if even for this very simple program, we could have multiple dimensions of inputs. So that's why the user input space is mostly considered as infinite. And given an infinite user input space, how can we effectively test the target program? So we need to do some observations. The first observation is that not all inputs have the same effect. So for example, for most of the programs, we could have valid inputs, we could have invalid inputs. So these inputs should be handled differently by the program. So not all inputs have the same effect. This is our first observation here. Our second observation here is we can partition the output. We can observe the output and partition the output of a feature into possible outcomes. So we can partition either the inputs or according to the outputs. So we can do the testing in a smaller space. So that's all about the basics of functional testing. And now let's jump into we will encounter partition very soon. And both of the techniques used here are using the knowledge of the theory of partition. Let's continue first. So for boundary, so we will learn two different types of black box testing today. So the first one is called boundary value testing. So actually the rationale of boundary value testing is that the density of defects is more towards the boundaries of programs. So like, I don't know if you play with lead code or not, but if you try to write algorithms on lead code, so what is the most tricky part? The most tricky part are the +1s or smaller than or equal to for loops or for recursions, right? So there are always some errors with off by 1 errors. So these boundaries are very important, and programmers are more likely to make mistakes here. So for example, they may misuse the operators of smaller than or equal to or smaller than. So whether should we put the equal sign here is a question mark. So this is very tricky for programmers, and of course different termination conditions for these for loops, while loops, and maybe some recursions may cause defects around the boundary value conditions. And sometimes the requirement may not be clearly understood, especially around the boundaries. So there are some unclear descriptions about boundaries. So boundaries are more likely to have bugs. So we should test around the boundaries. We should build our test data, our test input around these boundaries. So let's use an example to show you, to demonstrate what is boundary value testing. So assume we have a program that accepts two variables, two integers. So the first one is x1 and the second one is x2. So both of them have certain boundaries. So x1 is between a and b, x2 is between c and d. So as you can imagine, this area, this shaded area is the valid input region for this program, and just ignore this small gap here. So it should be filled up. And for boundary value testing, before we jump into how can we actually build test cases to explore the boundary values, to try to play with the boundaries, we need to first understand one assumption here. So this assumption is called the single fault assumption. So the single fault assumption is that failures are not triggered by multiple faults simultaneously. So this assumption means that we assume that a failure is only related to one specific parameter, but not two simultaneously. So this may not make sense for you, but let's do this assumption first, and then I will answer you why do we need this assumption. So let's assume that all the failures are related to only one variable. And just now we have a program with two variables, and that's our assumptions here. So with this assumption, it means that when we do testing, when we generate the test input, what we do is we hold all the values, all the variables normal, and we make one variable invalid. We insert errors into one variable every time. So not inserting errors, sorry. We assume extreme values close to the boundaries for one variable at a time. So we have different types of boundary value testing. So the basic idea of boundary value analysis or boundary value testing is to assume that the input variables are at their minimum, just above the minimum, at their maximum value, or just below their maximum value. So we can use these notations to represent these situations. So norm here means just taking the normal value, and if we draw it on the graph, it is like this. So in this figure, we can see there are test inputs. So each dot is a test input for this program, and we can see there are test inputs exactly on the boundary. So they are the inputs representing the variable values at their minimum or maximum, and we can see some dots are slightly below or above the boundaries, and these values are those which are smaller than the maximum value or slightly bigger than the minimum value. So these are the boundary values we take. But do you think this covers all the test cases we need for this normal boundary value testing? No, I see someone shaking the head. Or not? So why not? Yes, there should be a normal one. So we should always test the normal values. And this is why you should come to the lecture or watch the recording, or at least play with the animation, because what you see on the slides is the dot in the middle is hidden by a white circle. And so we should have all the 5 values and the combinations of different situations for both x1 and x2 to conduct normal boundary value testing. So these are the test cases needed for this type of testing. And another type of testing is called robust boundary value testing. It is an extension of normal boundary value testing. So in addition to the mean, max, slightly above mean, slightly below max, and normal, we should also test invalid inputs. So in order to test robustness, this time we create invalid inputs which are out of the boundaries. So just now all the dots are either on the boundary or within the valid area. But now we have 4 more dots that are outside the boundaries. So this is called robust boundary value testing. This is the second type of boundary value testing. So as you can see here, we have 2 more types of values to be included in our test inputs. And we have our third type of boundary value testing that is called worst case boundary value testing. Because just now, remember, we have an assumption that every fault is related to only one variable. But what if we remove this assumption? What if we allow a fault to be related to the extreme values of 2 or more variables? So what kind of test cases should we have now? So let's do a level poll and check if you could understand if you could understand what we have learned. So you can scan the QR code or check the link. So according to this definition, so we allow more than one variable to assume their extreme values that are close to the boundary or on the boundary. So what will we have in this case? What should we have? You can check our previous slides on robust boundary value testing. So this is the robust boundary value testing. So it controls only one variable. At most, one variable can take the extreme value here. At most, one variable can take the extreme value here. But what if we remove this kind of restriction? What will happen? What are the test cases that we should have? Let's check the results. Most of you choose the last one, and it is actually the correct one. So congratulations. So the last one, so according to the definition here, if we remove the restrictions of only allowing one parameter or one variable to take the extreme value, we are actually occupying the corners here. So this worst case boundary value testing here, it means that we can allow both values to take the extreme, to be close to the boundary. But remember, if it is not the worst case boundary value testing, if it is just the normal boundary value testing, we only allow one parameter to take the extreme value. So it means that they cannot be close to the corners, because otherwise both values will be close to the boundary. So if you remove that, we will have this figure. We will have these test cases. And what if we combine the term robust and worst case together, which means that we don't have the assumption of single fault. So which means that we allow multiple variables to take extreme values. And for robust, it means that we need to have some invalid inputs. We need some values to be outside the boundaries. So can you imagine how does it look like? So now we allow more than one values to be extreme, and we allow invalid values. So can you imagine how does it look like? So it will cover everything. So it will have all the dots we have seen before. So this is the robust worst case boundary value testing. And now, as you can see, there are some patterns, right? Actually, these patterns, the number of test cases we need for each type of boundary value testing is determined once we have fixed the number of variables to be tested. So the first one is, so assume we have n variables. So for normal boundary value testing, we need to create 4n plus 1 test cases. And what about robust boundary value testing? How many test cases do we need in this case? Oh, that's very fast. Did you see the slides? No? Okay. It's actually 6n plus 1. We will have 2n more test cases. What about worst case boundary value testing? So we need to cover every corner. We allow all the variables to take their extreme values. So how many test cases do we have here? Some of you are counting the so 5 to the power of n, yes. It's actually the Cartesian product of all these extreme values, or the normal values for the variables. So it's 5 to the power of n. What about worst case robust boundary value testing? You are doing it before you are trying. So it's actually the Cartesian product of this set. So it's like min minus plus max plus all the rest of the worst case boundary value testing. So if this is 5 to the power of n, then this one should be 7 to the power of n. That's a lot of test cases to have. So that's why, although it may not make sense that to have the assumption of single fault, to have this kind of single fault assumption, and to assume that each time only one variable can take the extreme value. So this may not make sense. This will make our test weaker, actually. But it makes sense to have less test cases. That is because we always need to meet the budget, and we always have a budget for us to meet. So that's why, although the single fault assumption weakens the overall test suite, it's covering less cases, but sometimes we still need to make such assumption. So that's why we need to have this type of assumption. And now, after seeing an example, let's do a practice. So in this practice, we are trying to test a triangle program. And this triangle program accepts 3 integers. All of them are integers, a, b, and c. So these integers are actually used as edges for a triangular. And the integer a and b and c must satisfy these following 6 conditions. So all of them should be between 1 and 200. And in order to make them triangular, they should satisfy the case that the sum of any two edges or size must be larger than the third one. And the output of the program. But this condition is this is somehow handled by the program. As you can see here, it is allowed to generate the output of not a triangle. So it should be, although the expected input from the user should be a valid triangle, but it is somehow handled by our target program here. And the rest of the program outputs are equilateral actually, isosceles and scaling. I searched the pronunciation for these terms before this lecture, and I found this term has different pronunciations in British and American pronunciation, right? So the Americans may pronounce it differently, and yeah, but let's just know these terms. So this one means two. So this term means all the three sides or all the three edges are the same, and the second term means two edges, two sides are the same, but the third one is different from the other two. And this one, the third one, means all the three sides are of different lengths. So these are the meaning of the outputs here. So now let's consider how can we do the normal boundary value testing. And in normal boundary value testing, we can assume all these 5 types of values for the variables a, b, and c. So what is the mean here? What is the value mean of mean? 1. Yeah. And what is a possible value for mean plus? 2. And what is a possible value for norm? Yeah, let's use 100. Let's just use the middle one to be safe. And what is the value of max minus? It's 199, and the max is of course 200. So now we have all these values with us. And if we remember how do we do the normal boundary value testing. So in normal boundary value testing, we have the assumption that only one variable can take extreme values at a time. So only one variable is allowed to take the extreme value. So what we can do is we can fix A and B to be norm, and let C take all these 5 different values. So in this case, we can have this form here. So we fix both A and B to be 100, and we let C take all the 5 values, and we will generate a table of test cases like this. What we can do is to so for B and A, we can do the same. So there's a typo here actually at A. So just now we have created the values for C, and we can do the same for A and B. So in the end, we will have a table like this. A table of 15 cases is 5 times 3. So, but you may ask, didn't we just learn that there should be 4n plus 1 or 13 test cases? So what went wrong here for this table? Just now we learned that for those worst case boundary value testing, the number of test cases required is the Cartesian product of the set of values available for these variables to take. So that's why it's 5 to the power of n or 7 to the power of n. But they didn't explain why this one is calculated as 4n plus 1. So why it is calculated like this? So what went wrong here? So we should have 13 test cases. We shouldn't have 15. So what's wrong with the table? So okay. Yes. Are you going to answer the same? Okay, good. So we have duplicated rows. We have 3 rows that are duplicate of each other. So these 3 rows are actually generated by taking the normal value for every variable. So that's why it's duplicated. So when we do this calculation for this formula here, so what we can do is we ignore the normal value first. We ignore the normal value. And then we have 4 different values for each input. So that's why we have 4n here. And this plus 1 comes from taking the normal value for all the variables. So that is why this formula is calculated as 4n plus 1. So this is why we do, so this is how this formula comes from. And before we jump into equivalence class testing, let's have a 15 minutes break. All right, guys. Let's start our second half of today's lecture. So, just now, I think one of you asked why is functional testing related to partition, right? So just now with boundary value testing, we have seen that we can separate the input space according to the boundaries. We can separate the input as minimum value or close to minimum value. Let's say a little bit above the minimum value, a little bit below the minimum, and the maximum value a little bit above the maximum, a little bit below the maximum. And this is one way of partitioning the input space. And here is another way of partitioning the input space, and that is called equivalence class. And the related testing technique is called equivalence class testing. So let's jump into this. So the rationale of doing this type of having this type of equivalence class testing is that we would like to have a sense of complete testing. So just now with boundary value testing, the process of generating the test cases is quite systematic, right? We are actually trying to go through every possible combinations of different extreme values of different variables. So it is somehow complete. But we want, for equivalence class testing, we also want the testing or the test case generation to be complete. So we want to have a sense of complete. And the second reason, the second desired testing suite here is we want to have a test suite with low redundancy. So this redundancy is different from the principles we have learned, the six principles we have learned in our last lecture. So remember, in our last lecture, we also learned the redundancy principle, and that principle is to use multiple different testing tools or multiple different levels of testing to test the target software. And this redundancy here means this redundancy here is a bad thing. So just now, when we go through the table of test cases generated, we could see if we don't do it carefully, we could have some kind of redundancies, like we could have 15 test cases instead of 13. So we want to avoid redundancies. We don't want to test. We don't want to generate test inputs that have the same effect on the target program. So here are the two considerations when we design a new testing strategy, and the design of equivalence class testing actually echoes the two deciding factors of boundary value testing. And remember, in boundary value testing, we have 4 different types of boundary value testing, and they are normal boundary value testing, and they are robust boundary value testing. So what's the difference between normal and robust? It is whether we have invalid inputs or not. So the first deciding factor here is called the robustness. And just now, the rest 2 types of boundary value testing are the worst case boundary value testing and the robust worst case boundary value testing. And the difference between the worst case boundary value testing and the normal boundary value testing is that is about the assumption of single fault. So just now we discussed why single shot assumption makes sense, right? Because if we don't have this assumption, we may have too many test cases. So the second deciding factor here is single or multiple fault assumption. So these 2 deciding factors are also affecting equivalence class testing. And remember, in in the triangle problem, the output of the program could have 4 different types, and according to the shape of the triangle. And actually, all these 3 inputs will give us the same shape, and that is equilateral. So all these 3 triangles are equilateral triangles. So that's so in this case, these 3 test cases should be treated the same, right? So equivalence class testing is actually to find whichever test inputs are equivalent to each other. And the key here is how we determine this equivalence. And there are many, like boundary value testing, there are many different types of equivalence class testing. And remember, the key here is how we decide the classes here, the equivalence classes here. And there are, the first type is actually not used nowadays maybe, but it is part of the history. So it's called traditional equivalence class testing. And in some of the standard texts, like those very old ones, I haven't read about them, but I just cited someone else. So in these standard testing texts, these the equivalent class are decided based on whether the input is valid or invalid. So actually, this is very close to weak robust equivalence class testing in modern equivalence class testing techniques. So the reason of focusing on invalid and valid testing in the old days is because by that time we don't have the programmers, they are coding in command lines, and most of the programs are command line programs, and they don't have graphical user interface even for the operating systems. And in that case, many of the user inputs are not limited. And nowadays, as the graphical user interface evolves, these graphical user interface could limit the user input options. So we don't have to do too much of input validation nowadays compared to the old days, because in the old days, let's say there's a command line user interface, and the user might be allowed to input anything from the keyboard, and the input validation takes a large chunk of the code for every program. So that's why in the old days they focus on the validity of variable values. So here's a step for doing traditional equivalence class testing. So the first step is that we test the function for valid values for all the variables that is accepted by this function. And if step 1 is successful, which means that the program doesn't run into a failure with all the valid inputs, we can continue to test the invalid inputs. And what we do is we still assume we still apply the single fault assumption, which means that we will keep all the variables valid, and only make one of them invalid, and then we test the program with this set of input variables. And we repeat step 2 for every variable here. So that is the basic idea of traditional equivalence class testing. And if we come to this x1 and x2 program. And this is how the equivalence class, traditional equivalence class testing looks like. As we can see here, we can, in the middle is the input from the first step. So that is a valid value of all the variables. And then for x1, we can test whether it is below the lower boundary or it is above the lower boundary. And for x2, we do the same. So, but do notice here that when we do this testing for x1, when we make it invalid, we still keep the value of x2 within the valid range, because this is somehow related to, this is somehow similar to weak robust equivalence class testing. So that's why. And this is traditional equivalence class testing. And nowadays we have improved equivalence class testing. So in improved equivalence class testing, what is improved? You may wonder, okay, what is improved? So what we improved is that we improved the definition of the equivalence relation. So in the old days, we only consider the inputs, all the valid inputs as equivalent, all the invalid inputs as another equivalence class. So, but now we could have more diverse definitions for equivalence, and that is what we have for these improved equivalence class testing, and which means that we can have more different types of sub-intervals for the test cases, for the test inputs. So assume we still use the program that takes two integers as the example here. So assume this program accepts two input variables which are still integers, x1 and x2, and they have the following boundaries. This time x1 is in between a and d, and it has three intervals: a to b, b to c, c to d. And the squared bracket means closed end interval, which means that a is included, and the parenthesis means it's open-ended, which means that b is not included in that interval. So here are the three intervals for x1, and for x2 we have two intervals. And you may wonder, how are these intervals determined for x1 and x2? Actually, they are determined based on the requirements, based on the actual implementation of the program. So we need to consider the actual scenario of this of the target program we are testing to determine the intervals. But in this example, we just use these three intervals for simplicity here. So let's continue. So from this assumption, we could have 5 equivalent classes for valid inputs. So these 5 equivalent classes are actually based on the sub-intervals of both x1 and x2. For x1, we have 3 intervals. For x2, we have 2 intervals. And if we combine them together, and that's all the equivalent classes we could have. And for invalid inputs, we could have 4 equivalent classes, and that is x is smaller than a, or x is larger than d, and the x1, and x2 is smaller than e, or x2 is larger than g. So we have, in total we have 9 equivalent classes, including both valid and invalid ones. So since we have the different definitions or different types of equivalent classes, Now let's jump into the first type of equivalence class testing. That is corresponding to the normal boundary value testing. Remember, in normal boundary value testing, we have the assumption of single fault assumption. We have this assumption, and we don't do robust testing, which means that we only care about the valid inputs. So in this sense, we have this graph of test cases. So do you think it is the correct one? It's not. You can see the color difference, right? I purposely made it differently this time. So it is. This figure is not correct. It's not following the definition here, because we are missing some intervals. So for the first one here, we need to consider, because we are doing weak normal equivalence class testing, we don't care about the invalid inputs. So we just care about covering every equivalent class. So what we can do here is we need to cover. Let's first consider the case of x1. So for x1, we can select a value from A and B. Actually, we can take the point here as well. We can put a point here, but that will give us a test case that covers G and F for x2. And let's assume we put a point here. And when we do the second point, because we only care about x1 now, so let's move on along the axis of x1. And after we have covered A and B, A to B, we now need to have a value in between B and C. Because we are covering E and F for x2, so now let's cover F to G for x2. So that's why we take this point. And for x1, let's continue to the third point to cover the third interval for x1. For x1 here, we should cover this point here. So do you think x1 for the last test case, we can put it right up here in this square? Do you think it is correct to put a point here instead of putting it here? Do you think it is correct? I see some of you nodding your head, and that is correct actually. We can put in any of these two squares for the last one, because our purpose here is only to cover the equivalence class for x1, and we have already covered all the equivalent classes for x2, so we don't need to care about the value of x2 in this case. So if so either we put it here or we put it here, both are correct. And now let's continue to the strong normal equivalence class testing. So strong normal equivalence class testing is corresponding to a worst case boundary value testing. That means that we remove the single fault assumption. So strong equivalent class testing is based on the multiple fault assumption, and we need the test cases for each. We need the test cases for each element of the Cartesian product of the equivalent classes. So because we still don't do robustness testing, we only care about the valid inputs, and we should cover all the combinations of the different equivalent classes for different variables. And in this case, we have two variables, and one of them has three equivalent classes, one of them has two equivalent classes, and in total we have 3 times 2, which is 6 we have 6 equivalent classes in total at the end for strong normal equivalent class testing. And now let's continue to weak robust equivalence class testing. And this term may sound counterintuitive, because how can a thing be both weak and robust? But actually the weak and robust here are not used to describe the testing technique itself. The weak here means it has the assumption of single fault. So each and every time a variable can only one variable can take the a particular equivalent class. And robust means we care about the robustness of the system, which means that we need to generate invalid inputs. And that is about the definition of this weak robust equivalent class testing. And let's do a live poll to see if this figure here is a valid weak robust equivalence class testing according to the definition here. Is this a valid one? You can also use the link here. Actually, I think I found something interesting. So this link here is actually, I think the last item in this URL is the item ID of polls. So in total, since the creation of WebCMS, they have created 1,668 polls, including this one. So I think in this term, we are going to contribute a lot of polls to the system. Let's increase the ID. So it is a valid one according to the definition. Oh, half. Actually, that is kind of expected, because this is not strictly valid. Why it is not strictly valid is because if we see this point here, this will make both x1 and x2 invalid, and it actually somehow breaks the term weak here. So it somehow breaks the term weak here. So it somehow breaks the single failure assumption. Somehow, and this point too. These 2 points somehow breaks the single failure assumption, because in these 2 points, for these 2 points, both x1 and x2 are taking invalid values. So what can we have alternatively? So this is what we could have that follows exactly the definition here. So instead of having a point here, we can separate it into 2 points. So in this point here, we do have some kind of redundancy for x2, but x2 is valid and x1 is invalid. For this point here, x2 is invalid, x1 is valid. For this point here, x1 is valid, x1 is valid, but x2 is not. And for this point here, x2 is valid and x1 is invalid. So in this example, we strictly follow the single fault assumption. So this is more ideal. And just now we have covered 3 different types of equivalence class testing. And now let's come to the fourth one. Because we have two deciding factors, and if we combine them together, we should have four different types of testing techniques. So the last one is called strong, robust equivalence class testing. So this means that strong means that we break the assumption of single fault. So we allow multiple values to be invalid at the same time. And for robust, it means that we care about the invalid values. So this will give us test cases from the Cartesian product or the combination of all the equivalent classes, including both valid and invalid ones. So this is what we will have in the end. So basically 1 dot per region, 1 dot per region for this strong, robust equivalence class testing. And this is only for, this is an illustration for a function with 2 input variables. Imagine if there are 3 inputs, we will have a 3D graph or a 3D figure here. If we have 4, we will have a higher dimension. So just now okay.
Just in general, does the word robust in the name, that means that not only are we testing that the good cases succeed, but we're also testing that the bad cases fail?
Yes, yes, yes. It means robust means we care about invalid inputs. So at least in this context, it means that. So it means that we will generate invalid inputs that are out of the boundary in the specifications.
So it's not like undefined, like when you practice memory outside C and you get undefined behavior, that's not robust because they're allowing you to do this thing that's undefined.
Yes.
But if they were to like throw an error or something,
Yeah, the program should handle that. Yes, yes. And you could have, but that's not the end. You could have different definitions of how the program should properly handle the error. So just throwing the error out may not be considered as acceptable. So yeah, that's the idea here. So just now we have covered 4 different types of equivalence class testing techniques according to 2 deciding factors, robustness and the single fault, whether should we follow the single fault assumption or not. And now let's come to a practice to apply these techniques. So here, in this, let's use the triangle program again. So in this triangle program, we could have these 4 equivalence class according to the output of the program. So the first one is the triangle is equilateral, and the second one is the triangle is isosceles. The third one is the triangle is scaling, and the last one is not a triangle. So let's first consider the weak normal equivalent class testing. So we have these 4 equivalent classes. So what we can have here is, I just give you the answer for this one. So what we can have here is, we can have 4 test cases just covering the 4 equivalence class. All of them are valid. All of them are valid. What about strong normal equivalence class testing? So do we need to consider the combinations of different equivalent classes? Actually no here. Actually no, because we don't have sub-intervals. just now in the example of x1 and x2, we have subintervals. We should consider different permutations or different combinations of different subintervals. But now here we don't have any subintervals. We only have four equivalence classes, and they are kind of independent to each other, so we don't have to combine them together. So the strong normal equivalence class testing, the test cases should be the same here as this one here. And you can see that actually these 4 test cases are enough to cover the real conditions we could expect from the user inputs. So for example, for a user input that is where A and B and C are all equal, it is actually captured by test case 1. And where A equals to A, but A doesn't equal to C, A equals to B, but A doesn't equal to C, and all these 3 are actually captured by the second one. And D5, it is captured by, assume it is still a triangle, it is captured by the third one. And D6 to D8 are all covered by the test case WN4. So as you can see, this design is quite complete. It's quite complete. It could cover all the real world scenarios we could encounter. And as for weak robust equivalence class testing, in addition to the previous weak normal equivalence class testing, we could have these 6 different test cases. So what we have here is we make the, because remember we do have value restrictions for A, B, and C. So what we can do is we can have invalid value for A, we can have invalid value for B, we can have invalid value for C that is smaller than their lower bound, and we could have A larger than its upper bound, B larger than its upper bound, C larger than its upper bound. But because we are doing a weak equivalence class testing, each one of the time only one variable is allowed to be invalid here. So in this case we have 6 test cases in total. So because each one of them has 2 invalid equivalence class, each one of them has 2 invalid equivalence class, and we have 3 variables. So in total we have 2 times 3, 6 test cases here. So what about strong, robust equivalence class testing? I won't show you the results in this time, and can you imagine what are the possible test cases we could have? So in this time, it is strong, robust, which means that we allow more than 2 variables to be invalid at the same time. So what we can do is we can have these test cases. So we can have A taking the value smaller than the lower bound, B taking the value smaller than the lower bound, C taking the value smaller than the lower bound, and A, B are both below the lower bound, BC are below the lower bound, and AC are below the lower bound, and all of them below the lower bound. We can have these test cases. And do you think that's all the test cases we could have here? No? Why? Yeah, we should have the valid ones. And that's all? Including the valid ones?
Valid test cases should be
actually, because this is actually only one corner. If we somehow draw a diagram, this is a 3D diagram, but so we only care about all the values smaller than the lower bound, but we didn't cover, let's say, all the values larger than the upper bound, and we didn't cover maybe one of them is smaller than the lower bound, the other two are larger than the upper bound. Maybe two of them are smaller than the lower bound, one of them is larger than the upper bound. So we are missing a lot of cases here. So this is only one corner in the diagram, you could imagine. So if we remove those assumptions, we will have a lot more test cases in the end. And now we finish the triangle program practice. Let's come to a second practice here. So in this time, we have a new function called nextDate. It is a function that accepts 3 different types of variables: month, date, and year. Day and year, actually. Month, day, and year. It returns the date of the next day as output, and it reads the current date as input. So the conditions here are: month should be in between 1 and 12, day should be in between 1 and 31, year should be, let's assume the year ends by this year. So actually, in reality, there are more restrictions than these 3 conditions. Can you tell me why? What are the additional restrictions we should have here? It's actually more complex than these 3. We can't do it here in this slide, in this simple example. That is more complex. In reality, it should be more complex. Yes, 29. So some years are leap year. So for February, yes, and for different months, for different months, there could be the upper limit for the day is not 31. And for February, it's more complicated because in leap year, February has 29 days. And it is also related to year, so we should have more complex conditions combining days and months and days and year. So that's in reality, but in this program, in this example here, let's just assume we only have 3 conditions. We only have these 3 conditions. So can you think about what are the valid equivalence classes here? What are the valid equivalence classes? How many valid equivalence class do we have? 3, yes. We only have 3 valid equivalence class. And we don't have sub-intervals in this example as well. And what are the invalid equivalence classes? How many do we have? 6. Okay, that's really fast. We have 6. And now we are clear about the valid equivalence class and the invalid equivalence class. Let's try to design the equivalence tests. So first, for weak normal equivalence tests, how many test cases should we have? Do we need to have? How many do we need to have? Yes. We only need to have 1. And it's the same for strong normal equivalence class testing. That's because they don't have sub-intervals. So each one of them has only has one interval. So we don't have anything to choose from. So that's why we only have 1 test case here. And for the weak, robust test cases, we need to consider we need to not only consider the valid cases, we should also consider the invalid inputs, which means that we should consider the equivalent classes of the invalid inputs. So what we can do is when we try to design the tests for the weak robust equivalent class testing, we can inherit the valid one first, and then we go through all the equivalent classes of all the equivalent classes of the invalid inputs. So what we can do is we inherit this one, and then let's consider the equivalent class of M2. What we can do is we can apply M2 here and generate a test case with an invalid month, and we can do the same for the rest of the test cases. So in the end, we will have 7 test cases for weak robust equivalence class testing, and this is because weak robust means that it is weak. We only need to make one variable invalid each time. So that's quite simple. We just consider one of them every time and apply the invalid equivalence class. What about the case of strong robust equivalence class testing? So we have these valid and invalid equivalence classes, and what can we do here? So we can of course we need to inherit the valid test case first, and after inheriting the valid test case, what we do is we apply the rules one by one. So let's only assume the lower bound case. Let's only assume the lower bound case here. So for example, what we can do is we can apply the equivalence class of month lower than the lower bound, month smaller than 1, and we can have this test case. Similarly, we can apply the equivalence class of day smaller than 1, and then we can have this test case. And we can also consider the equivalence class of year smaller than 1900. So this will give us another test case. And what else should we do next? We have finished the test case generation with all the inputs, with only one invalid inputs. So what we do now is we make 2 of them invalid at a time. So what we can do is we can first consider the case by making both month and day invalid, and this will give us this test case. And we can consider to make both day and year invalid, and this will give us another test input. And what we can do is we can consider making it test case. We can consider making both month and year invalid, and we can have this. So the last one, as you can imagine, is to make everything invalid, and we can have this test case. But is that all? No again. This is only a corner again. So because as you can see from the line connections, we only consider the case where everything is smaller than their lower bound. We don't even consider the the case where everything is larger than the upper bound, and we don't consider the different combinations here. And actually that's all for the content today. And before we end our lecture, let's quickly go through what we have learned today. Because if you have learned about the memory rules or some psychology things, you know, if you try to recall something you have learned like 10 minutes ago or maybe half an hour ago, it's much easier for you to memorize everything. So let's have a quick recap of what we have learned today. So first we have learned the concept of functional testing, and it is actually some kind of black box testing. And for black box testing, it is also known as specification-based testing. And because we want to tag the functionalities according to the specifications. And for the specifications, do you still remember the difference between a specification and a requirement? So a specification is like more like a detailed or a more verifiable requirement. So that's a specification. And functional testing is to derive test cases according to these specifications. And the key principle to be applied in functional testing is called partition. We want to partition the input space. We want to partition the output space. And we learned two ways of doing this partitioning. And the first one is to use the boundary value to do the partitioning. And the second one is to use equivalence class to do the partitioning. And for boundary values, we could derive it from the specifications. For equivalence class, we could either follow the traditional definition of using valid or invalid, or we could derive different sub-intervals according to the specifications or the actual case. And for these two types of testing, for boundary value testing, for equivalence class testing, both of them, they have two deciding factors. And the two deciding factors are robustness and the assumption of single fault. And by combining these two deciding factors, we can have 2 times 2, 4. And that is 4. We have 4 different types of testing techniques for boundary value testing and equivalence class testing. For boundary value testing, we can have normal boundary value testing, we can have robust boundary value testing, we can have worst case boundary value testing, we can have worst case robust boundary value testing. And for equivalence class testing, if we do the same thing, we could have weak normal equivalence class testing, we could have strong normal equivalence class testing, we can have weak robust equivalence class testing, and we can have strong robust equivalence class testing. And I hope you can remember maybe all of them, and that's the best. And as you can see here with these practices, it is almost impossible for us to do this thing manually, but there are clear patterns, and it's very systematic. The process is quite systematic, so it could be easily automated with programs, and that's what you are expecting to do in your assignment 1. So that's it for today, and thank you.生日快乐，生日快乐！我想问一下，明天你还有 明天没有，明天
那我明天我过来了。
好，
是3点、2点。
2点。
2点。
好。
I'm quite curious. So these are mentioned in these techniques are mentioned in literature, but are they really used in practice that often? Because I've working at a company, I've noticed that there's not many times I can see.
For these, but these are not like particular engineering problem. So they are more like those high-level concepts that will affect your design of, let's say, unit tests, let's say system tests. So when you design unit tests, you should consider the boundary values, right? When you design unit tests, you should also consider to use equivalent classes to cover different cases.
Right.
So these are more like
principles.
Yeah, principles or those high-level basic concepts that could be applicable to different specific techniques.
Okay, yeah.
So you will encounter this a lot when
Yeah.
you think about how to design different concrete test cases.
That makes sense. And also, you may have mentioned this, but I didn't get how we end up like because when we do the improved equivalence class testing, and we make it not multiple equivalence classes, what qualification do we give to those equivalence classes? Like, why would we choose? Like, why not choose like 1,000 equivalence classes? Like, what is important about each equivalence class? Do we choose them arbitrarily or like?
Not arbitrarily, as in the triangle problem, in the triangle program problem, we are actually separating the equivalence class according to the output of the program.
Right.
So we may need to consider either the specification or the output when we actually do the equivalence class separation.
So it's kind of like a guess to say like the program, like with these inputs, so with that equivalence class, the program's probably going to take the same kind of control flow. Roughly.
It's not a guess in real life. It shouldn't be a guess because we are given the specifications, and the specification will tell us what are the input ranges or what are the expected outputs.
But it's a guess in that like we're thinking about like if we're thinking about the control flow, we're thinking about the implementation now. And we're trying to say that
that's more like structural testing. We will cover that next week. Okay.
Okay, thank you.
Thank you.
So just looking at the course outline, and I noticed that there's weekly quizzes. I couldn't find that anywhere.
This is not our latest plan. This is something from the e-course quiz, right? You should follow the.
So there's only 2 quizzes the whole
Yeah, there are only 2 quizzes.
Just 2 the whole time?
Yeah.
Oh.
You can find the latest plan in the link. I updated the link of course outline on the web
So
CMS.
this is for 2024.
So this is actually this is our plan. This is our plan and the correspondence of different topics with different assessments.
Okay. Yeah. All right.
And you'd better find a team to do assignment to.
Is it possible to do assignment 2 individually, or do you need?
You can do it individually.
Okay.
You can do it individually, but if you could manage it.
Okay.
Manage.
So if I can manage, I can do it individually.
Yeah. Yes.
Okay.
Yes.
That's fine.
Yes.
Thanks a lot.
Okay. See you. Bye bye. 冷，今天不知道为啥，我感觉上次还挺热的，这次又冷了。我在想怎么设计第2个assignment。反正主要让他们分享组的话，到时候有问题。
我觉得这个歌好认真
really